Okay, let's get started. Is there some vacation that's going on right now? Holiday? Or is this normal for this time of the year? It's what? Or are these topics too boring? Of course, you wouldn't say no since you're here. But then people who are not here don't get to vote either, so. Say it again? Oh, they can watch it online. Yes, that's right. I guess. Do you guys feel that way? Because you have the lectures online, you prefer not to be here? Maybe I'm asking the wrong crowd, but. Say it again? Many do, okay. I guess that's fair. I mean, in the end, it doesn't matter as long as people learn the material. I don't have a problem with that. Of course, I prefer not to lecture to an empty room, but I've done that before. I recorded my lectures in front of a camera without students being there. It was really awkward, and you can find them online, and I don't like that. I'd prefer to lecture and then record, and then it's easier to see that energy, I think, that way. Okay, so yesterday we covered something really exciting. I think all of the lectures are exciting to me, so I'll be repeating this exciting part all the time. But we ended up with a Dataflow graph, if you remember. So let me do this. I'm not going to go over that again. Out of order execution. We've gone through a very detailed example of how an out of order execution machine operates, based on Tomasulo's algorithm. And we've seen basically, by the way, all of these slides in the nicer form are posted. The cycle-by-cycle execution that we went through, it's already posted as PDF. Basically, we've executed this code. I'm trying to find this code over here, right? And then we've gone through it cycle by cycle. At the end of cycle 7, everything gets renamed. And once you observe the state of the machine over here, you can actually form the data flow graph because you know exactly which registers are going to be produced by which instructions in which reservation stations. You know exactly which instructions need which registers, well, which values at least, and which other instructions are going to produce those values. Now you can actually, if you remember the last part of the lecture, by looking at just this, constructed this. And from here, you can go back and construct most, if not all of this. And I'll leave you that exercise. It's not that hard. Basically, you can know which instruction. So this is an add, for example, that takes R4 as input and R3 as input and produces A. And I don't remember if we, let's see. Where is that thing? Yeah, A. Huh, interestingly, you don't have the A over here, right? Where is A? It was already overwritten. That's excellent, yes. So that's the tricky part of reconstructing it. It was already overwritten by this over here. The key question is, can you figure that out? What do you think? You know that it's already overwritten because there's no register. You know that it's overwritten by one of these, right? Or one of these 5. But do you know which one? Can you guess? You do? What's the trick? If you don't answer, I'll leave you with it so that you can have fun and figure it out on your own, because I think it helps to figure it out on your own. Anybody? Yes?
Can we take it from the source? There we have its own connection, D and A. Yeah, what is it?
Yes. So basically, D is instruction that's producing, instruction that's at the reservation station. D is reading A and Y. It's clearly writing to D. So you know that A is alive at this point, right? by that instruction. So it read A, and then it wrote to D. But then somebody else may have written to D also. So that's the point, basically. I think you're definitely onto the right thing. This instruction read A, and A doesn't exist over here, but then it wrote to D. So A existed before this instruction got into the machine, but after this instruction got renamed, A doesn't exist anymore. So you can conclude that that instruction overwrote the register that it read. Do you agree? Yes. So that's basically the trick here. That way you can actually say, oh, this instruction that's reading R3 and R4, which is easy to determine, is writing actually to R5, which was renamed to D after it read A. Okay? So that's how you do the reverse engineering. And once you know what's going on, it's so easy. So you will feel that it's fun, actually. And you can find bugs in it also. Okay, so I think we've covered the trick, which is fun. So let me go back to the slides over here. So basically, the point over here is you have the data flow graph in the machine, which means that implicitly the out-of-order engine actually constructed this data flow graph without actually having a graph. Right? That's why out-of-order execution is a restricted form of data flow execution internally. And I'll show you that more carefully. Basically, we were covering out-of-order execution. We're going to be done with this today, and we're going to move on to other execution paradigms. I call this the approaches to concurrency. These are basically instruction-level concurrency. Still, we're at the instruction level, mainly. And people have tried to exploit this instruction-level concurrency in many ways. So hopefully, you'll get a glimpse of it. So remember, there are 4 things in out-of-order execution that enables it: linking, buffering, tracking readiness, and waking up and selecting. You just need to remember the red parts over here, or dispatch, I guess. Linking is done by renaming. Buffering is done by inserting instructions, moving instructions out of the way into the rest areas, reservation stations. Keeping track of readiness is done by broadcasting the tag and instructions comparing that tag, that complicated logic that we went through. And it is complicated. And hopefully this gives you an example of how complicated it is to build a data flow machine, right? This is a restricted part of the window. You're really limited to the reservation stations that I showed you over here. We have only 4 reservation stations here and 4 here. And 11 registers in this case over here. Now imagine doing it for 1,000 or thousands of instructions. That becomes very complicated very quickly. And you can analyze the complexity, but we're not going to do that in this class. And waking up and selecting is also necessary to fire the instructions in data flow order. Okay, I'll just keep these in the slides, but that's for your benefit. So we did the exercise without precise exceptions, with imprecise exceptions. That's how we got the execution, 20-cycle execution. And one of you pointed out that actually you don't need the write-back stage, and that's actually true. The way I described it, you don't really need the write-back stage, because at the end of the last execution cycle, you broadcast the value and tag, and that gets latched, and the instruction is done, assuming you have imprecise exceptions. Right? You don't need a separate write-back stage after that. I'm trying to find those things over here, but I'm not being very successful. Now, where is it? It has to be somewhere. What do you think? Okay, that's fine. You remember the basically execution timeline. I guess I didn't bring them with me. Okay, one last shot. Okay, there it is. Last shot is always good. Okay, let's go back to this. Remember, we were broadcasting instructions at the last, broadcasting the tag and value at the last execution cycle for an instruction. And at that point, the register file is also latching the value. So we really don't need a write-back stage over here. So that's correct, actually, if you have imprecise exceptions. If you have precise exceptions, then you will need to write it over here somehow, and then ensure that you write in program order, right? So that's why we have the reorder buffer. So you'll need to add the reorder buffer on top of this. But we're not going to do that. You can combine the concepts in your head. Otherwise, it starts getting complicated quickly. But this is I'll leave this as an exercise. How long will this take in an in-order dispatch pipeline machine with a reorder buffer, with no forwarding and full forwarding? And how long will this take in an out-of-order dispatch pipeline machine with a reorder buffer with full forwarding? It's easy to do. Once you know how out-of-order execution and a reorder buffer works, it's easy to combine the concepts. Okay, so let's move on, if I can. I don't know. So turn off and turn on works. There you go. Okay, basically, how do you combine them? You use a reorder buffer to reorder instructions before committing the instructions to the architectural state. An instruction updates the register alias table when it completes execution. That's exactly what we've done. This is also called a front-end register file. Basically, you have a register file in the front end. I guess I'm not going to go back and forth. Instead, I'm going to show you. This is the register file, right? Front-end register file. That enables renaming. But if you have a reorder buffer, you need to really have another register file. Right? So most machines today have a separate architectural register file that is updated when the instruction retires. So this front-end register file that's used for renaming is updated when the instruction finishes execution, when it broadcasts its tag and value. But this architectural register file is updated in order, in program order. Whenever you commit an instruction that's at the head of the reorder buffer, that instruction updates the architectural register file. So now you have two register files. Basically, when the instruction is the oldest in the machine, has completed execution, it updates the architectural register file. In other words, you guarantee that this register file always has the precise state because it's always updated in program order whenever an instruction gets out of the reorder buffer, in program order. So it's pretty simple. So on an exception, what do? You flush the pipeline, and you basically copy the architectural register file to the front-end register file and make all of the registers valid. Right? Because you've updated the architectural register state in program order. All the registers are valid. Once you flush the pipeline, you clean all of the other instructions that are potentially writing to the registers. And now you can copy the architectural register state to the front-end register state and restart execution from the point where you want to start. You're at a precise state at that point. So today's machines work this way, actually. With one exception, they don't store the registers. They store pointers to the registers. Okay, let's get back to this. Basically, we looked at this part a lot, scheduling part. It's done by the reservation stations. And we looked at the reordering part. It's just now in this slide, even though we didn't go through a detailed example of it. You can imagine how it works. Okay, there's nothing else I want to say in this slide other than the fact that an out-of-order machine is really out of order in this part, right? So we preserve the von Neumann model. We fetch instructions in von Neumann order, sequential order. We retire instructions in von Neumann order, sequential order, but internally, it's completely data flow. There's no ordering of instructions other than other than the ordering that's dictated by data dependencies. True data dependencies, that is. Okay, so, let's look at a modern processor. Most modern processors use the following that I will describe. You have reorder buffer to support in-order retirement of instructions, and a single register file to store all registers. Basically, if a register is written again, you actually have another copy for that, another location in the single register file for that register. If you have R2, for example, written by multiple instructions, they allocate different physical registers. This is called a physical register file. So it contains not only the speculative registers or renamed registers, but also architectural registers. So you have the architectural state inside the single register file. Of course, when I say single, I think about integer and floating point separately. So usually the integer and floating point pipelines are separate in an existing processor. So you have a single physical register file for integer registers, and you have a single register file for floating point registers. Now, we're not going to cover floating point that much in this course, but that's another data type that's dealt with by processors today. So what does this mean? Basically, now, how do you do the renaming? You rename an architectural register to the name of a physical register that you allocate to it. So basically, you have this architectural register file that gets renamed to the physical registers file. I'll show you a picture of how Pentium 4 does it soon. Okay, there are two register maps to imitate front-end versus architectural registers. One is front-end or future register map. This is used for renaming. That's at the beginning, basically, register alias table. But you take out the values from it. You don't have the values inside there. You just have the pointers to the physical register file. And an architectural register map that's used for maintaining precise state. Okay, before I go into it, I don't want to destroy this one, but I can destroy this one. So basically, what we have is the front-end register alias table looks like this. I'll call it FRAT. But we won't have values, so I'm going to remove the map, front-end register map. Let's call it that way. And then you have a single physical register file that could be huge. Let's say 256 entries over here. And then this basically maps the architectural registers to the latest names. Basically, it maps the architectural register to the latest instruction that's fetched in the machine that's going to produce that register. For example, R0 over here could be mapped to a physical register, I don't know, 55. R1 could be mapped to physical register 2, ... and you have a mapping. This is used for renaming. Basically, this is called front-end because it shows the state of the mapping with all instructions in the pipeline. And you also have a back-end register map, or what do they call it? Back-end retirement architectural register map. This is updated, this map is updated only when an instruction retires. Basically, when an instruction retires and if it's writing to R0, and if its physical register that was assigned to it was, let's say, 34, it basically says, oh, R0 was pointing to, let's say, something else over here. Now I'm writing to it, and the data value that I stored is at physical register 34, so I'm going to change the mapping of R0 to physical register 34 because I'm updating the architectural state. Make sense? So you don't store the values in the architectural register file, but you store pointers. That way you don't need to carry the values around a lot. You store all of the values in one place, but the value becomes architectural only when the instruction finishes execution and retires. Make sense? Basically, this is an optimization. That way you don't have values here, but you have pointers. So you can think of these as pointers to architectural registers in the physical register file. And this is the pointers to last renamed registers in the physical register file. It's pretty clever, right? Okay, so let's go back. The approaches we've covered look like this. Basically, this is, it's called NetBurst, but it's really the Pentium 4 that Intel implemented. But it's really done in all high-performance processors that I know of. They basically have a front-end register alias table and a retirement or architectural register alias table or register map. And they basically keep pointers to it. And if they want to recover architectural state, now it's pretty simple again, right? If you have an exception, retirement register alias table has the pointers to the architectural registers. You flush the pipeline, you copy these pointers over here, and you're done. That way you can restart from a precise state, because now your front-end register file points to the retirement, points to the same registers as your retirement register alias table points to. Okay? And Pentium 3 does it in a little bit different way, although they also use pointers so that they don't carry values around. So in their they store data in the reorder buffer, and they store data in the retirement. They still have an architectural register file over here, and a register can be named, can be present either in the register file or the reorder buffer, as we've seen before, right? So this is an optimization such that you don't need to have a separate register file over here, and you can have a single register file. Okay. Okay, I'm going to move through this because hopefully you know all of this now. So I guess this is, again, another redundancy. These are important concepts. Basically, renaming. Why do we do renaming? Because it eliminates false dependencies and enables linking of producers to consumers. If you do buffering, it enables a pipeline to move forward without stalling on a dependent instruction. We can enable independent instruction execution. Tag broadcast enables communication of readiness of the produced value between instructions. And wake up and select enables out-of-order dispatch. So those 4 things over here enable everything that you need for out-of-order execution. Okay, let's go back to the data flow. Basically, I said out-of-order execution is a restricted data flow machine, right? Out-of-order engine dynamically builds a data flow graph for a piece of the program. Which piece? I think I've already given you the answer. The piece that's limited to the instruction window. Basically, all of the instructions that are in the reservation stations at that moment, you can reconstruct the data flow graph for them. All decoded but not yet retired instructions, basically. Can we do it for the whole program? Well, I guess you could have a huge instruction window, right? Like 1 million reservation station entries. Of course, this is very tough to do. That's why this is very hard to scale to very large parts of the program. I guess, first of all, why would you like to? It's always good to ask, why would you like to do it for the whole program, right? And the reason here is latencies, right? If you have very long latencies, you want to be able to process independent instructions while you're waiting for that operation. So if you have a 1,000 cycle memory operation, it'd be good to have lots of instructions you can process in parallel. Maybe not the whole program. But whole program, if you do it for the whole program, you enable parallelism, right? You can execute many, many instructions per cycle. How can you have a large instruction window? These are more questions for you to think, basically. Can you do it efficiently with Thomas-Lowe's algorithm? And the answer is no. Because of all those tag comparisons, all those buses that run around the machine, right? You need to wire those buses. They need to go to all parts of the machine. And this is just a toy example, right? I mean, it's not toy from Thomas-Lowe's machine, but it's very similar to Thomas-Lowe's machine circa 1965. But you only have 4 entries, the reservation stations here. But if you'd like to scale this up to 1,024, now you have lots of comparators here. And they're working every cycle. Every cycle you do the comparison. At least every cycle when you broadcast something. Okay. So modern machines actually do a lot of clever techniques to optimize this. And one clever technique we just saw, actually, this is a clever technique to have a single register file instead of having copies of registers everywhere in the system. But we're not going to go through those clever techniques. If you really want to know that, take the advanced architecture course. Okay, so let me point out one other thing over here. Basically, this is really a data flow graph that we constructed from this state of the machine. But it is a real data flow graph. If you think about it, nodes are the operations performed by the instruction. Arcs are the tags in Thomas-Lowe's algorithm, right? Really, we have assigned tags to the values that are communicated between instructions. So if you think about the data flow that we've discussed, you basically have input tokens. Tokens are really these values that are named to the physical registers. Right? These are our tokens, and whenever 2 tokens arrive at a data flow node, the node fires and produces another token, which means that writes to another register or broadcasts its value with that name, and then that goes to the instruction that needs that token, if you will. Okay, so hopefully that's clear. Basically, it's nothing different from data flow. So let's talk about some questions to ponder. So this lecture last lecture was very implementation oriented. We walked through how an out-of-order machine works. This lecture will be more conceptual. So why is out-of-order execution beneficial? Remember that I foreshadowed this question. What if all operations take single cycle? Would you benefit from it? No, right? There's no latency to tolerate. Basically, out-of-order execution tolerates the latency of multi-cycle operations by executing independent operations concurrently. If there's no latency to tolerate, you don't need to execute out of order. In fact, if the compiler is really perfect in ensuring that all of your latencies are tolerated by making sure that long latency instructions are followed by enough independent instructions, there's no need for out-of-order execution. Right? But we remember the last lecture, compiler could be very good at doing that, assuming it can find independent instructions, and assuming it knows the latencies. And both of those are difficult for the compiler to do. Okay, so what if an instruction takes 500 cycles? Now this becomes interesting because this is really the problem that existing out-of-order machines are having. Memory latencies are so long that whenever you get a cache miss, it could easily take 500 cycles and even much more. For example, in Xbox 360, which is really old today, a single memory access was about 650 cycles. And that was not the highest frequency machine at the time. And it's easy to see the memory access latencies go up, and they're going up for various reasons, which we may get to, because there's more contention in the system also when you put more processors into the system. So the question is, how large of an instruction window do you need to have to continue decoding? Well, if you're fetching one instruction per cycle, and if you're waiting 500 cycles, maybe you need a 500 entry instruction window if you want to keep decoding, right? Assuming there are no other non-idealities. And that's a lot. Now, if you're fetching 4 instructions per cycle, which is what existing machines do, we're going to talk about, and if one of the instructions stalls for 500 cycles, now you need an instruction window that's of the size 4 times 500, so that you don't waste any slots, if you will, in the machine. So that's, you don't stall at all. That's 2,000 instructions. That's a lot. So a lot of, okay, I'm going to skip that. Well, maybe I'm not going to skip that because this goes into some other questions. But basically, a lot of the research that's going on into, and also design that's going on into the design of these machines try to get the performance of a large window without actually having to build that large window. And how do you do that? Well, you want to minimize the latencies. That's one example. So you focus on the memory system such that you minimize the number of times that you see these long latencies. Okay, how many cycles of latency can out-of-order execution tolerate? Basically, depends on the size of your window, how many reservation stations you have, how big of a reorder buffer you have, how big of a register file you have. If you think about it, these are all decoupled, and they all need to have enough entries so that you can keep progressing and fetching instructions and decoding instructions. What limits the latency tolerance scalability of Thomas Low's algorithm? Again, the window size, active or / instruction window size. And this is determined by both the scheduling window and reorder buffer size. If you remember that picture with 2 humps, the scheduling window and reorder buffer, they both determine your latency tolerance. Because reorder buffer, if you don't have enough entries in your reorder buffer, you cannot decode an instruction. Because you need to allocate an entry in the reorder buffer to do the reordering at the end. If you don't have enough entries in your reservation stations, again, you cannot decode an instruction, right? These entries are allocated decode time. So a lot of the research that's gone into these machines try to really aggressively utilize these entries. How can we minimize the number of entries? We deallocate them very, very quickly such that we get many, many instructions into the machine, such that instructions don't hold on to those entries. So you can imagine how to optimize some of these things, perhaps. So I'm not going to go over a lot of the next slides. This is just to show you example processors, but this is your reading. By the way, how many of you have read this reading? No one? Okay. I was going to ask if it's interesting, but if no one has done the reading, it's going to be hard to ask that question. Has anyone done the reading? Don't be shy.
Which reading?
Oh, this microarchitecture of superscalar processors. No? Okay. Well, that's okay. I would recommend that you do the reading because some of the concepts here will become more clear. And the textbook really doesn't have these topics, really, which is a limitation of the textbooks, not a limitation of, yeah, basically these are concepts that exist out there. Okay, so I'm going to not walk you through this, but this shows you the complexity of an existing machine. You have caches and you have basically different register files, floating point and integer, instruction buffers. Instruction buffers are called reservation stations, and reordering and commit, and there's a memory interface which we haven't talked about yet still. But this was Intel Pentium 4. This is a nice paper. If you have time, read it. You're not going to be responsible for any of this material that I'm showing you right now. But this is just to show you the complexity of the machine. Some of these you will hopefully recognize. Some of these you won't recognize. So microcode ROM is one example. You will hopefully recognize micro-op queue. Basically, they can Intel fetches micro-ops and basically allocates micro-ops. Actually, it renames micro-ops. So basically, it does everything in the micro-op fashion over here, as opposed to x86 instruction level. You translate x86 instructions to micro-operations, micro-instructions, and rename those micro-instructions, and then send them to different queues, if you will. These queues are queues that feed into the schedulers. So remember I said that they want to minimize the size of this logic where you do the tag matching. So they try to minimize the scheduler size or reservation station size as much as possible. So they have different kinds of schedulers here. This was the FP scheduler, and there are also complex FP scheduler, which we're not going to talk about. But you can see how many schedulers you have, and when they broadcast across all of them. So that complexity actually becomes high. And as you can see, you can have the register file over here. So they put the register file in different places because that turns out to be better. And bypass, you see the bypass network, it's forwarding logic that we've seen. They call the network because it's really a network. It's lots of wires to bypass values across these different functional units. And you can see they even have different types of instructions, ... Okay, you're not going to be responsible for this, but just know that it's complicated. Again, if you want to know all of the components, that's the advanced architecture class. This is my drawing of Intel Pentium 4 simplified based on one of my papers. I like simplifying it this way. I think this is not so clear. But basically, it looks like this. You have this front-end register alias table, and after renaming, so you fetch the micro-operations. After renaming them, you put them into different queues. These are FIFO queues, such that you can decouple different parts of the machine. And then you put them into the schedulers. This is where the out-of-order dispatch happens. And then they read the registers, and they go into the execution units. And there's a reorder buffer. And they basically, at the end of execution, they broadcast their values, but we don't show that over here. Alpha 21264, this is a nicer picture, potentially. This is a recommended reading. Again, you don't have to do it, but if you're interested, this is a good reading. So it's a cleanly designed processor, but it looks very similar, basically. Register rename. These are the schedulers over here, and these are the register files that I mentioned. So remember, they have the renaming map. They don't get the values at that point because the register maps don't have the values. So they read the register file to get the value later. That's why the register file sits here. It's clean because there's only one point where you read the registers, which is over here. Right? At least the register file. And then you can also get the values from the bypass path, of course. MIPS are 10,000. Remember the MIPS? MIPS was designed such that hardware would be simple. Well, there you go. It's actually very, very similar to Alpha 21264. The original philosophy of MIPS, if you remember, microprocessor without interlocking pipeline stages. Every dependence detection is done by the compiler. Well, not so in existing machines because that's too low performance. So to get performance, they do exactly the same thing, register mapping. And you can see that they do some allocation here, free register lists. Other pictures don't show it, but all machines look similar. Okay, IBM Power 4 is similar also, and these are some readings. If you have interest, you can look at it. So IBM Power 4 is actually a little bit aggressive for its time. This is 2002. And they had a 100-entry instruction window, 8-wide instruction, fetch, issue, and execute. So they can fetch 8 instructions per cycle. This is Superscalar execution, which we're going to talk about. And you don't need to understand everything over here, but all parts of the machine is big. IBM Power 5 adds multi-threading to it. If you remember multi-threading, fine-grained multi-threading, they basically have 2 program counters, 2 different instruction buffers from 2 different threads, and 2 different store buffers, and they don't show it over here, but 2 different register maps somewhere over here, but they don't show it. Okay, so hopefully that gives you an idea of how a modern machine operates. Now you're really almost up to date, except for all the bells and whistles that people have added to out-of-order execution to make it much more efficient. But let's look at some alternative approaches. So this is not the only approach, out-of-order execution, but currently it's the dominant approach. Except for the GPU space, which we will also talk about. So these are some approaches. Basically, data flow at the ISA level, we're going to go back to that a little bit. So out-of-order execution is data flow at the microarchitecture level, right? ISA is still von Neumann, sequential, easy. People have looked at data flow at the ISA level. This is not ordered in the way I want it, so I'm going to do out-of-order execution on these slides. We're going to talk about superscalar execution after the data flow. But let's look at the data flow. This is more of a review because we talked about data flow, if you remember. What was it, lecture 13? I think it's lecture 13. But data flow is really good at exploiting irregular parallelism. You build a data flow graph, and whatever parallelism you have over there, if it's irregular meaning, this will become more clear when we talk about regular parallelism. Irregular means there's no pattern to the parallelism. An instruction wakes up another instruction, and some other instruction may be waking up some other instruction. The dependencies are not easy to see. As opposed to regular parallelism, for example, if you're adding two arrays together to each other, element by element, this is very regular, right? You're doing an add, you're repeating that add on all of the elements of the arrays. If you're copying one string to another string, and you're repeating that copy on all of the elements of the string, that's very regular. And there are much more efficient methods to actually take advantage of that regular parallelism, which is SIMD processing, which we will hopefully get to later in the later part of the lecture. But data flow is good at irregular parallelism, where you cannot say, oh, all of these things I can do at the same time. You basically, it's good because availability of data determines the order of execution. And if you remember, a data flow node fires when its sources are ready, and programs are represented as data flow graphs. As long as you give it the data flow graph, data flow nodes, it just ensures that enough, the parallelism in that data flow graph is exploited, right? The problem is data flow at the ISA level has not been as successful, and we'll talk about why very briefly, because it's very hard for the programmer to reason about them. If your instructions are this graphical data flow representation, remember the precise exceptions? If you get an exception in a machine, now the execution can be anywhere. There's no precise state because there's no program counter, right? You cannot even define a precise state. In fact, if you define a precise state in a data flow machine, and if you make it work, you may be very rich, first of all, and second, you may get the Turing Award. But it's very tough to define that precise state because by nature, there is no ordering, right? And ordering is useful for reasoning. If you're a programmer, at least if you want to reason about something, you'd like to have it in a consistent order. You don't want a program to have one order when you execute it and it crashes. And when you're trying to debug it again, you don't see that order. Well, maybe you don't even see the bug the next time, right? So that's the problem over here. So data flow, however, data flow implementations under the hood, without being exposed to the programmer, meaning while preserving the von Neumann sequential ISA semantics, have been extremely successful. And out-of-order execution is a prime example, basically. All machines, high performance, do this, except GPUs. So let's look at the advantages and disadvantages of data flow based on this. Advantages, basically, it's very good at exploiting irregular parallelism. In fact, probably it's the method that we know best today that exploits irregular parallelism, instruction level parallelism. You can exploit that parallelism really well. Because only real dependencies constrain processing. There's nothing else. You don't impose a program counter. Whenever you impose a program counter, you're imposing an artificial dependency to the operations, which means that you're reducing your parallelism. Disadvantages, of course, there are many others that I'm not going to go into, and this requires really advanced understanding of data structures and how you implement them on data flow. Those are the ... over here. But one of the biggest disadvantages is debugging is very difficult. There's no precise state. And as a corollary, interrupt and exception handling is also very difficult. What is the precise state semantics? And and data flow machines become very large because you need to have a lot of things. So it's basically difficult to design these machines. So it's high bookkeeping overheads. There's a lot of tag matching and data storage. So out-of-order executions are a limited part. If you expand it to 1,000 instructions, a huge data flow graph, now you can see the bookkeeping overhead. And too much parallelism is another issue, actually. People, when they tried to build these machines in the 1970s, 1980s, early 1990s, they figured out that parallelism can go out of control quickly. because you have a data flow graph and you enable execution of many, many instructions at different times, and you need to store them somewhere. And storing them somewhere is difficult. First of all, that leads to the high bookkeeping overhead. And whenever a dependency resolves, many instructions get enabled. How do you control that? Right. So this is a real problem. So it turns out there's a lot of parallelism in existing programs. You just need to express it in a data flow graph, but controlling it becomes a problem. Okay. So, okay, this is the right ordering. Now I fixed the ordering over here. So maybe we should dynamically fix the ordering over there too, but that's okay. So let's go into superscalar execution. I assume that this is an easy concept. So far we've been looking at scalar execution, meaning one instruction fetched per cycle. Superscalar is a very simple concept. You fetch, decode, execute, and retire multiple instructions per cycle. That sounds simple, right? N-wide superscalar means you do n instructions per cycle. Which means that you need to add hardware resources for doing so. You need to be able to decode multiple instructions. You need to be able to retire multiple instructions and everything else. If you don't provide those resources at any point in the pipeline, that pipeline stage becomes a bottleneck. And you know, based on the principle of balanced design, you should never do that. Right? If you're fetching, if you have the ability to retire 20 instructions per cycle, but if you're fetching one instruction per cycle, you should never expect higher performance than one instruction per cycle. And people have made these mistakes, actually. I still review papers that come to me that have these imbalanced designs, and they have this bottleneck, and it doesn't make sense. Right? So you need to have a balanced design if you want to retire n instructions per cycle. Okay, so superscalar is hardware. Basically, hardware performs the dependence checking between concurrently fetched instructions. If you're fetching 4 instructions per cycle, they're written in an order, so you need to perform the dependence checking, right? Now this complicates the machinery. Okay, this is very important. Superscalar execution and out-of-order execution are completely orthogonal concepts. Out-of-order execution refers to in what order do you process the instructions, execute the instructions. Superscalar execution refers to how many instructions do you fetch and retire. And you can combine, have all 4 combinations. In order, out of order, times scalar, superscalar. So, for example, I'll pick one. In-order scalar machine, Intel 386 was an in-order scalar machine, for example. In-order superscalar machine, Intel Pentium, the first machine that had the Pentium name, was an in-order superscalar machine. It was in order, it could fetch 2 instructions per cycle, but it couldn't reorder instructions at all. It would stall on a true data dependency. Out-of-order scalar, those machines exist also. I don't have a good example, I guess. But it's easy to think about. Basically, the machine that we looked at, right? We were fetching 1 instruction per cycle, but we were doing out-of-order execution. And many machines today are out-of-order and superscalar, and that's exactly the reason why people confuse these concepts. Whenever people talk about superscalar execution, sometimes they really mean out-of-order execution, and sometimes vice versa, which is unfortunate, I think, but we're at ETH here. We should not make that mistake. Basically, out-of-order superscalar, you fetch multiple instructions per cycle, and you can execute instructions out of order. So let me give you one example of an in-order superscalar processor. Basically, you need to have multiple copies of the data path. In this case, this is, remember, the simple pipeline that we had. Register file, you have multiple ports such that 2 different instructions can access 2 different ports. 2 different instructions can write at the same time. And 2 ALUs such that 2 different instructions can execute in this pipeline stage. 2 different address ports to the register file. 2 different write data ports. And 2 different read ports coming out. That way you enable multiple instruction execution. One single PC, that way, because you address that PC and you get 2 instructions, right? Not only this instruction, but the next sequential instruction as well. Now, what is the first instruction you're fetching as a branch? Well, you're implicitly making the prediction that the next instruction is the next sequential instruction. But if you were really doing superscalar execution, and you had a lot of branches in the code, that becomes a problem. So now you have intricacies in the machine. If you're fetching 16 instructions per cycle, it's likely that you're going to get a branch in the middle. And assuming consecutive instructions may not be a good idea. Let me finish superscalar execution and we'll take a break. Basically, superscalar execution complicates the fetch engine a lot also, in addition to requiring resources over here. So dependencies make it tricky because now you need to check there's an older instruction and there's a younger instruction. There are 2 instructions. By the way, there are 3 ports over here because you need to have a write destination write port also somewhere here. But this may not be the best figure. That's okay. What was I going to say? Basically, you need to check whether the later instructions can execute when this instruction is fetched. I'll give you an example of this. And this becomes complicated as you increase how many instructions you're actually fetching. If you fetch 16 instructions per cycle, think about that dependency check logic. You'll need to check all of those dependencies in one cycle or multiple cycles. Basically, dependency checking takes a long time. It's really a tree of dependencies, right? Because any instruction can be dependent on the previous instruction, and you need to know those. Now, if you were doing out of order, not in order, you need to be able to rename those at the same time. So that logic becomes very complex. So Intel, for example, right now is fetching 4 instructions per cycle, and they're doing renaming on those. Okay, here the ideal IPC is 2. Let's look at an example. Ideal IPC is 2 because, in this case, all instructions are independent of each other. Well, at least the 2 instructions over here that you're fetching at a time are independent of each other. That's good. So IPC is the inverse of CPI, instructions per cycle versus cycles per instruction, right? You could view it both ways. Superscalar performance with dependencies quickly goes down. This is in order again. So if you look at this, you fetch this load instruction, but you cannot really issue the add instruction in the same cycle, which means that you really lose a slot in the superscalar execution. You can only send 1 instruction over here because the next instruction that happens to be in the instruction streams is dependent on the previous. So you can issue 2 here because these 2 are independent, but then, well, this is fine, I guess. Even though this is dependent on this one, it has to be issued in the next cycle because you can only send 2 instructions per cycle. But here, there's another problem over here. Well, basically, those are dependencies. But these 6 instructions, you can issue only in 5 cycles. So actual IPC goes down to 1.2 over here. And as you increase the width of your superscalar engine, the probability of you hitting these dependencies increases. So you get into a diminishing return. So if you look at a performance curve, usually as you increase the width of the superscalar, with the N that I mentioned, your performance looks like this. It flattens out at high N. Now this means that if you have a superscalar machine, a compiler can help, right? Even though we're doing everything in hardware, dependency checking, the compiler, if it reordered the instructions nicely on a superscalar in-order machine, you would perhaps get 2 IPC, right? So that's why the compiler is actually useful in in-order execution. A superscalar out-of-order machine could do better, of course. So let's finish with this, trade-offs. Advantages, you get higher instructions per cycle, higher instruction level concurrency. That sounds good. Disadvantages, you get higher complexity for dependency checking. Basically, you require checking within a pipeline stage. And renaming becomes more complex in an out-of-order processor because you don't look at it into time only, but also in the space at the same time. More hardware resources are needed, clearly. And I guess that's it. Shall we stop here, or shall we leave you early today instead of having a break in the middle? What do you guys prefer? So let's we'll do it democratically. Who wants a break right now? Oh, okay. Well, who doesn't want a break? It's almost equal, so I'm going to favor the people who want a break because they may really need that break for some reason. But it's a short break. It's only 10 minutes. Yes.
I have a question regarding the function call in x86. Okay. There is the enter instruction.
Okay. Looks like we've lost some people during the break, or they're coming in. So now you know of superscalar trade-offs. There were a lot of interesting questions in the break, so I'm going to go back to a modern processor, again, to stretch your mind very quickly before we move on to something else, just to show you how things are optimized. Yeah, if you look here, and we did this in the Tomasulo example, the out-of-order execution example, we had a separate adder and a separate multiplier, right? So a lot of modern processors actually have separate functional units. Well, in this case, for example, they specialize this functional unit. They call it ALU, but it's really simple, very, very simple instructions. And there's an ALU that's slower, that's for complex instructions. So integer multiply, for example, goes here, integer add goes here. The reason for this is instead of having a single monolithic ALU, you have two different ALUs specialized for different functions. Now you can actually optimize this a lot, right? You can make an adder really fast without worrying about, oh, how does the multiplier also operate and how do I combine these two things together while achieving the cycle time. In fact, Intel Pentium 4 had this really interesting concept. They had different clock domains in the processor. So the clock that was running over here was actually slower than the clock that was running over here. And that was also slower than the clock that was running over here. So there was a normal clock. I think they called this the medium clock or something like that. Which was, let's say, 1x frequency. The front end was running at 0.5x frequency, but they were fetching 6 instructions, 6 microoperations per cycle. So they could get 3 microoperations per cycle at the 2x clock. And then they could actually execute this 2x at a 2x higher frequency. So they optimized this ALU so much that the frequency over here was about 6.8 gigahertz. As opposed to the 3.4 gigahertz frequency that they had over here, and the front end was about 1.7 gigahertz. So if somebody tells you that 10 gigahertz is a dream, that's not true. They were already almost at 10 gigahertz over here by optimizing the ALU. Of course, power consumption is a different issue, right? That's which we will not talk about. But if you look at a modern processor, you'll see a lot of interesting things. And we're not going to be able to cover all of those concepts in this course. But we'll cover VLIW, which is essentially superscalar execution done by the compiler. Which sounds interesting, right? But we're going to add more constraints. So if you look at superscalar concept, hardware fetches multiple instructions and checks dependencies between them. Some people had the idea of, again, why don't we keep the hardware simple and push the job to the compiler? Very long instruction word, VLIW. So software or compiler packs independent instructions in a larger instruction bundle. Now that's your instruction really, long instruction, such that they're fetched and executed concurrently. So now I'm going to redefine my instruction concept. My instruction is really 3 operations, and those 3 operations are independent, and the compiler figures out what those 3 operations are and puts them together, such that I can fetch 3 operations per cycle in every cycle. Now you can redefine it to be 28 operations, 56 operations. You fetch 56 operations per cycle, and it's the compiler's job to figure out the dependencies. Sounds good, right? The beauty of this is, so hardware fetches and executes instructions in the bundle concurrently, but hardware doesn't need to have the dependency checking logic in the VLIW model, because software already did the hard work to fill those instructions into the bundle. Okay, so basically, we're going to contrast this with SIMD later on, but we'll look at it later. But basically, a very long instruction word consists of multiple independent instructions packed together by the compiler. And packed instructions can be logically unrelated. They can be completely different. Add, multiply, load. Add, store, multiply. As long as they're independent, that's good. Now, we're going to contrast this with SIMD later on, hopefully in this lecture. SIMD is an execution model where you can also fetch multiple instructions, if you will, multiple operations, but you only do add, but on different data elements. It's still multiple operations. It's more restricted in that sense compared to VLIW. So, I mean, I've given you the idea, basically. Compiler finds independent instructions and statically schedules or packs or bundles them into a single VLIW instructions. So traditional characteristics, you want multiple functional units, multiple instruction fetch. Each instruction in a bundle executed in lockstep. So you don't want to do any dependency checking. Basically, if any instruction stalls in a bundle, all of the instructions stall. That keeps the hardware simple, again. We want simple hardware. Think about the MIPS concept. Basically, this is the MIPS concept in the scalar version applied to the multiscalar or multiple superscalar version, right? An instruction in a bundle can be statically aligned to be directly fed into the functional units. So you can make the hardware really streamlined. So for example, if you have an adder and a multiplier, the compiler says, I'm going to put the add here and multiply here such that when the hardware fetches them, they directly go into the functional unit. If you have an adder, multiplier, divider, the compiler orders the instruction such that it matches the characteristics of the hardware, such that you don't need to do any movement of the inputs, operands, between this part of the machine to this part of the machine, because it so happens that you fetch the instruction here, but then the adder is somewhere over here. The compiler aligns such that the place where you fetch the instruction is where you execute the instruction. That's a very powerful concept, actually. So this is the conceptual view of thinking about it. You have a program counter, still it's von Neumann. But whenever you index your memory with your program counter, you get a bundle of instructions instead of a single instruction. You get these 4 things. And these 4 things, you can fetch them, and then you can supply them directly into the processing elements or functional units. And these functional units can be specialized. This could be an add unit, this could be a load unit, this could be a move unit, and multiply units. But then, of course, they could do multiple things as well. So this concept was introduced by this paper. It's actually a beautiful paper, nice to read paper. Josh Fisher was the inventor of the concept, and he writes nicely, I think. He called it actually enormously long word instructions, ELI 512. So 512 bits instructions. MIPS that you're looking at has 32 bits, right? Okay. You're not required to read that. So basically, VLIW performance example is very similar to Superscalar performance example, except the compiler has bundled these things together, and they're at the same program counter over here. But now you can hopefully get 2 instructions per cycle if the compiler does a good job finding instructions that can be executed concurrently. Okay, so lockstep execution. Let's spend some time on this. Basically, lockstep means all or none. If any operation in a VLIW instruction stalls, all instructions stall. And the instruction completes when all of the operations are done. So now you have a problem. If you have a load instruction and an add instruction together, if this load takes 500 cycles, the add also takes 500 cycles. Right? That's been one of the problems with the VLIW machines. They cannot deal with the latency very well, variable latency very well. So in a truly VLIW machine, the compiler handles all dependency-related stalls, and hardware does not perform dependency checking. It's a beautiful concept again, right? Just like the reduced instruction set computer that we talked about. You have very simple instructions, very simple hardware. Compiler does the hard work. Hardware does almost nothing. So hardware is simple, hopefully. What about variable latency operations? Well, these cause a problem anytime you have a statically scheduled machine, static scheduling, where compiler needs to reorder instructions. Variable latency becomes a problem, as we've discussed earlier. So VLIW machines clearly had this problem with the variable latency, and we're going to cover that. So philosophy is very similar to RISC, as I've just discussed. You have simple instructions and simple hardware, except you add multiple instructions in parallel on top of that. That's what VLIW is. So RISC, a little bit of history, RISC was developed in the late 1970s in IBM by John Koch. IBM 801 mini computer was that. Compiler, again, does the hard work to translate high-level language code to simple instructions. In fact, John Koch's vision was you translate it into the control signals. Compiler does all the hard work to generate the micro instructions, in fact. It knows all of the hardware control signals. It generates them. Such that hardware doesn't need to do anything, right? It just fetches the control signals and sequences through the control signals. And compiler reorders the instructions for high performance. So hardware is very simple, so you can make it hopefully very high frequency. It does little translation because compiler actually went all the way down to the translation level. Okay, so later this became popular, certainly at Berkeley, for example, Spark was developed for RISC, and MIPS was developed at Stanford. And then MIPS that you're seeing is a variant of the MIPS that was developed in the early 1980s. So VLIW was developed a little bit later with a very similar concept. Compiler does the hard work to find instruction-level parallelism. Hardware stays as simple and streamlined as possible. Each instruction in a bundle operates in lockstep. So hopefully you get simple, higher frequency, and easier to design. So there have been commercial processors with VLIW. In fact, some of them you may be using if you're using, I don't know, some of these embedded systems like TI embedded systems. But there were some experimental prototypes that were designed to be 28 byte. So you could fetch 28 instructions per cycle, which is really unheard of in a scalar instruction processing model. With SIMD, you can do that, as we will see. But with completely independent, different instructions, you don't have this. And there were others also. For Transmeta Crusoe, we talked about this before, right? What they did was they actually took x86 instructions as their ISA, but then they had a software translation layer that translated that x86 to an internal VLIW instruction set that was executed on their hardware. So they had this code morphing software, which I mentioned some lectures ago. They basically wanted this to be much more efficient than an x86 processor that was designed in hardware, because they would do it internally via VLIW, but it turns out that software overhead was too much. It was reasonably power efficient, but performance was not there. So I'm not sure if Transmeta exists anymore. Has anybody heard of that? I don't think they do, actually. But it was a very cool concept at that time. This was late 1990s. And actually, most successful VLIW engines were in digital signal processing and embedded processor domain, because you could actually optimize your code, and codes are relatively simple and static in those domains. So a lot of the embedded time-critical systems, for example, if you have an automotive control system, you don't want variable latencies. So you want to optimize for worst-case latencies over there. Now you can statically schedule your code for that worst-case latency. So VLIW is a really good fit in those kinds of systems, because you know all the latencies in your system. So a lot of real-time systems benefit from very long instruction word machines. They can exploit parallelism while keeping the hardware simple, because the model that you have, fixed latencies, is good, is applicable there. So most successfully, VLIW has been commercially in those domains. So there has been an experiment that Intel did, unsuccessfully actually. IA64 was an example VLIW engine, but it was not fully VLIW actually, but based on VLIW principles. But it really confounded the principles, if you will. So the idea, we don't need to go through this in detail just to give you a history, but in this case, they violated the VLIW principles. What they wanted to do is they wanted to move to 64-bit ISA. So all of the registers are 64 bits, addresses are 64 bits, as opposed to 32-bit ISA. And while they were moving to 64-bit ISA, they also said, oh, why don't we change the ISA completely? That sounds bold. It's a good experiment. I think from Intel's perspective, it failed. But it's definitely a good experiment to do once in a while in companies. So they wanted simpler hardware also. So they actually had VLIW-like instructions. They called it EPIC, explicitly parallel instruction computing. And instruction bundles could have dependent instructions in that case. So they could specify the dependencies internally within a bundle. And that complicated the machine way too much. We don't need to go into detail here, but if you take an advanced architecture course from me, we can go into the detail of why this failed. But one of the reasons why it failed is it departed from so it wanted not to fail, because traditional VLIW mostly failed in the general purpose domain, and we'll talk about why. So they added these dependencies, so compiler can specify the dependencies between instructions in a bundle. But that turned out to be very difficult to manage in the machine. It's a lot easier to design out-of-order machine that could actually figure out those dependencies, as opposed to compiler providing these dependencies. So you wouldn't get much benefit, basically. Okay, so just to give you the history over here. Okay, let's look at the advantages and disadvantages of traditional VLIW, not this IA64, which is kind of in between VLIW and Superscalar with some compiler hints. So the advantage is there's no need for dynamic scheduling hardware. Now, compiler does everything. Reorders instructions, fetches multiple instructions per cycle. No need for Superscalar dependency checking hardware as well. So this is out of order, this is Superscalar. You don't need any of that, basically. No renaming, again. Actually, that's not fully correct, because a lot of the compilers rename as well, but we're not going to go into that. So if we had time to talk about, they do renaming at the software level, not at the hardware level. Okay, but there's no hardware renaming, so hardware is really simple. And no need for instruction alignment and distribution after fetch to different functional units. So if you have different kind of functional units, and if you fetched an instruction and it needs to be executed in this functional unit, you have a complex network to satisfy this in hardware. You don't need that network if you have VLIW, because all of the instructions already align nicely to go to your hardware directly. So sounds good. Disadvantages, as always, this is always a disadvantage. Compiler needs to find n independent operations per cycle for a given cycle. But if you want to actually get the full advantage of VLIW, you also need multiple cycles, right? You need to fill the machine, its width, as well as its depth. So if you can actually support 2,000 instructions in the machine, you need to be able to ensure that you can schedule 2,000 instructions at the compile time. But certainly, within a cycle, you need n independent instructions. And all of the other stalls, you need to fill with independent instructions. It turns out it's hard. So if it cannot, it inserts no ops in a VLIW instruction. So if you have a 28 wide VLIW machine, what people found out was you had a lot of no ops in that 28 instructions. Right? You really want 28 useful instructions, but if you have 20 no ops and 8 useful instructions, then maybe it doesn't work so well. Okay. So this leads to not only parallelism loss, but also code size increase, because you're including no ops now in your code, right? So this has an impact on your performance as well. If you're not encoding your no ops wisely, you lose performance. And initially, VLIW machines didn't encode their no ops wisely. So one way of encoding no ops, if you have 20 no ops consecutively, you don't have no op, no op, no op, no op, no op, right? But you say, I have 20 no ops coming. And the hardware knows that 20 no ops are coming. Instead of fetching 20 useless instructions, you say you have a pointer basically saying, oh, 20 no ops. So you basically inject no ops in the hardware. But that still causes code size increase. So you could eliminate this, but it still leads to increase. And actually, there are other reasons why code size increases, which we're not going to get into. If you want to schedule instructions in a graph, you'll need to move instructions in the boundaries of the branches, which means that you'll need to add code to undo what you do if you take the branch in the other way. We've discussed this briefly last time, but we're not going to go into the detail. Okay, the other downside of a VLIW machine is if you change the machine, if you, let's say, your first generation was 4 wide, 4 instructions per cycle. Next generation, you want 16 instructions per cycle. You need to recompile, right? Whenever you change the execution width, whenever you change the instruction latencies, because you tied your code intimately to the microarchitecture. Whenever you change your functional units. That sounds bad. I mean, it may still work, but you may not get the benefit. So this is very much unlike superscalar processing and out-of-order execution on top of it, because whatever code you throw at superscalar out-of-order, it'll try its best to reorder instructions to limit the performance, to maximize the performance, right, by finding independent instructions. But now you're relying on the compiler to find the independent instructions, so if you change your machine, you'd better recompile your code. So this is true any time you tie your performance, your optimizations to the microarchitecture, specific microarchitecture you need to recompile. And lockstep execution causes independent operations to stall. No instruction can progress until the longest latency instruction completes. So these were the disadvantages. And because of these, even though VLIW simplifies hardware, it requires very complex compiler techniques. And even with complex compiler techniques, it didn't become very successful, at least in the general purpose domain. So solely compiler approach of VLIW has several downsides. Again, too many no ops, not enough parallelism discovered. Static schedule is intimately tied to the microarchitecture. Code optimized for one generation performs poorly for next, and it may not even execute for next if it's relying on exact instruction latencies. And if you don't, when you change the microarchitecture, if you don't account for past code that was written for a previous VLIW microarchitecture, right? If you do account for a previous VLIW microarchitecture, now you're complicating the hardware. You're going against the principle, right? Okay. And no tolerance for variable or long latency operations. The upside, the huge upside of VLIW has been in compiler technology. Basically, most compiler optimizations that were developed for VLIW are in your compilers today. They were initially developed for the VLIW to make this thing work. But now it's very good for superscalar out-of-order machines because you get a lot more efficiency if the compiler is intelligent and reorders the code such that independent instructions are everywhere, right? So if you do GCC -05, for example, you get a lot of these optimizations. And VLIW is successful when parallelism is easier to find by the compiler. Traditionally, embedded markets and digital signal processors where you have these either real-time requirements or static latencies, not variable latencies. So there is a benefit. There's an advantage to it also. So hopefully this stretches your mind a little bit more as well. I think it's a cool concept. It's always good to think about, like, what do I want? This is a very principled design, right? If you think about these two concepts, well, superscalar plus out of order, I'll put over here. Because VLIW as a concept, it's not just multiple instructions per cycle, but the philosophy itself is all of the ordering is done by the compiler while you're doing multiple instructions per cycle. So it combines superscalar plus out of order concepts at the compiler level. Whereas superscalar plus out of order, the philosophy, the principle is, I'm not going to rely on the compiler at all. Whatever you throw at me, I'm going to find the independent instructions. This principle is exact opposite, right? VLIW. I'm not going to rely on the hardware at all. Well, other than knowing it. But I'm going to orchestrate everything myself such that the hardware remains simple. And I'm going to make the best of the hardware. So the question is, can you find middle points? I think this IA64 attempt of Intel was very courageous in that sense because it tried to find that middle point. But I think it failed, unfortunately. But that's okay. There are a lot of jokes about it, but maybe you don't make it here. Okay. But it was a very good concept. Actually, a lot of technology that was developed for VLIW compilers went into the IA64 compilers. But even that was not enough to make it work, to make it successful in the market. So Intel actually abandoned the effort, I think. IA64 is probably being sold in very, very high performance markets that got latched into it. So it's a really small market for Intel right now. But their vision was to actually replace x86 with this IA64. Okay, so let's move on to another cool concept, which is SIMD processing. And this is, again, a very widely successful concept. It was not as widely successful before the GPUs. It was relatively specialized. But this hopefully gives you another historical perspective. Times change, constraints change, applications change, and different execution paradigms may be really useful. And I think we may be seeing that with systolic arrays, as I mentioned earlier, right? Google TPU, Tensor Processing Unit, uses systolic arrays, for example. But we'll talk about that when we get to it, if we get to it. So far we've talked about irregular parallelism. VLIW is also for irregular parallelism. The compiler is extracting parallelism out of this mess of code. Actually, compiler works with the data flow and control flow graphs also and tries to figure out what's independent and dependent. But if the parallelism is regular, you can do something much simpler. So what is a regular parallelism? So let's put a taxonomy into the computation paradigms. This was actually done in 1966 by Mike Flynn, who's retired at Stanford now. But basically, he categorized computer instructions in terms of how many instructions you execute and how many data elements you execute on. So you can have single instruction or multiple instructions, and you can have single data element and multiple data elements. So a single instruction operates on a single data element. This is exactly the ISAs that we were looking at, right? Add instruction operates on a single data element. Whenever I say a single data element, it's really a single scalar data element. So it's really two data elements, but that's it, basically. You add two values. It's not like an add specifies two additions on two pieces of data, two different pieces of data, or for the elements. Basically, you specify only one operation for an add. Single instruction, multiple data. Single instruction operates on multiple data elements. You don't say only do an add of these two numbers, but add these two sequences of numbers, these two arrays, basically. So you can say you're doing this operation on 1024 different sets of elements. So we'll see array processors and vector processors, and a modern GPU is a combination of both, actually. MISD is a weird concept. Multiple instructions operate on a single data element. So you do add, multiply, or something on a single data element, or a single set of data elements. It's a little bit harder to imagine, but closest form is really systolic array or a streaming processor that we will hopefully get to. But you don't need to bang your head into the wall about it right now. Yes? Okay.
Division of two, like for example, 10 divided by
I see. Okay, so then you have multiple data elements, you say? Uh-huh. Okay, I see. That's a good point, actually. Yeah, I have not thought about that. You can have very specialized forms of these operations that require multiple instructions on single data. Yes, but you can always break that down into multiple instructions also. Yes. Yeah, you could also think about that also. Yeah, exactly. But we'll see this historically. So there's arguments as to whether this exists or not. And actually, Flynn's taxonomy didn't talk about that as much. So MIMD is multiple instructions operate on multiple data elements. This is multiple instruction streams, basically. So multi-threading, multiprocessors are really examples of the multiple instruction on multiple data elements paradigm. So they can execute completely independent instructions. So VLIW is an example of SysD, actually, because you really have a single logical instruction, right? You can specify multiple operations, but it's really a single logical operation. And it's lockstep, right? So the instruction doesn't move, even if you complete one of the logical operations. It's really an entity together. So we're going to cover this one. I mean, the advanced architecture course will cover a lot of multiprocessing, and we'll figure out what to do with that. So this is also data parallelism. Basically, in this case, the concurrency doesn't arise from something else that we're going to talk about, but it really arises from performing the same operations on multiple pieces of data, different pieces of data. For example, a dot product of two vectors, or addition of two vectors, matrix multiplication. You're really doing the same operation. Let's do the dot product, basically. It's really doing multiplication on multiple different elements, right? And then addition at the end. But if you're adding two arrays, that's again SIMD, right? If you're copying one string to another, that's SIMD, because you're doing the copy operation many, many times. So contrast this with Dataflow. In Dataflow, concurrency arises from executing different operations in parallel. It's really different operations. You don't care about whether they're the same or not, whether they're using the same data element or not, or different data elements or not. It's really data-driven execution. Contrast this with thread or control parallelism. Here, concurrency arises from executing different threads of control in parallel. And whereas SIMD exploits instruction-level parallelism. You have multiple instructions, or more appropriately, operations that are concurrent. Instructions just happen to be the same in this case. Okay, let's take a look at that. So this could happen in time or space. There's this time-space duality, and you need multiple processing elements. So let's look at the time-space duality. So array processor, an instruction, a SIMD instruction, operates on multiple data elements at the same time using different processing units, using different functional units, using different space, basically. We'll see an example of this soon. On a vector processor, an instruction operates on multiple data elements in consecutive time steps using the same processing element. So now you see that a vector processor is more frugal in terms of its hardware usage. You have a functional unit, and you have a SIMD instruction that's, let's say you're doing an add, and you're doing that add on multiple elements of the array, two arrays. Every cycle, you look at a different data element. You add a different data element. In an array processor, every cycle, you do different additions. You do the same addition on different data elements on different processors. So let's look at an example over here. So this is an array processor. You have multiple different processing elements that can all do the same thing. Whereas you have a vector processor that have specialized units, load, add, multiply, store. And we're going to look at this code. And this code looks interesting now because the input over here is an array, right? It's a 4-element array. You're going to load this into a vector register, which consists of 4 elements. Actually, let's take a look at this. So we're going to assume registers are not scalar anymore, but they're really vectors. They store multiple. So basically, you have a vector register, 0, which can store, let's say, 64 elements. 0 through 63. So if you're doing an addition of array A to B, what you can do is you can load 64 elements into vector register 0, and then you can load 64 elements of B into vector register 1. Okay, like this, I guess. And you have a functional unit, add, and then you basically, in consecutive cycles, send one element per cycle to the functional unit. That way you do 64 additions in 64 cycles, right? That's it, basically. So it's pretty simple. With one instruction, you specify 64 operations. So it's very efficient. That's why the GPUs are very efficient, because they don't have this control overhead. If you think about a single instruction, single data machine, all of these are different adds. It's a different loop. Basically, you do this in a loop, right? Whereas here, we have a single instruction that basically specifies a 64-element loop in a single instruction, single data machine. So if we go back to this example, basically your vector register is 4 entries, and you load the first 4 elements of the array into the vector register, and then this add happens to add one element, increment each element by 1, and this multiplies each element by 2. So you basically are incrementing each element by 1 and then multiplying that by 2. So what you're really computing for each element is 2 times x plus 1, right? 2x plus 2 in the end, and then you're storing the results into back into the memory. Yes.
I don't understand why the vector processor should be any faster than a single instruction machine. I mean, the processor still has to check, still has to do a loop, it still has to go over 64 elements one by one.
Okay, it'll be clear when we go through the performance example. We'll go through a performance example soon, but let's clarify the concepts here. So an array processor, here if you look at this, you have one load instruction operating on 4 different data elements. You can do all of those 4 different data elements operations at the same time. You load element 0, you load element 1, you load element 2, you load element 3 concurrently into the vector register. In the next cycle, you add 1 to element 0, add 1 to element 1, 1 to element 2, 1 to element 3. In the next cycle, you multiply element 0 with 2 and do the same thing on different elements. And the next cycle, you store the results into the different the corresponding locations in memory. So that's the array processor. It's beautiful, right? You're operating with just one instruction. You're doing 4 operations here. Vector processor is the same thing, except you're doing it in time. You load the first element. You're finishing one instruction across time. You load the first element over here, and then in the next cycle, you load the next element. Basically, you're pipelining the load. In the next cycle, you're adding the first element, incrementing the first element. In the next cycle, you're loading the next element, adding the first element, and multiplying the 0th element. In the next cycle, you're loading the third element, adding the second element, multiplying the first element, and storing the 0th one. So this is the steady state where all of your functional units are now busy. And then, of course, you finish the pipeline. So a vector processor is a little bit longer, as you've observed, but this is going to be still faster than a normal machine. And we'll see why. But an array processor does same operation at the same time, whereas a vector processor at the steady state does different operations at the same time. And if you look at the space, meaning different functional units, an array processor does different operations in the same space. That's why it's more expensive. Whereas a vector processor does the same operation at the same space. So a vector processor is a little bit cheaper because your functional units can be different. They don't all have to do the same thing, right? They don't all have to do all of the operations, as you can see over here. Okay, so let's contrast this with VLIW. So remember VLIW, with one single program counter, you fetch multiple operations. These could be independent operations, and they're packed together by the compiler, and logically they're a single instruction after that point. In an array processor, a single operation is encoded this way. You have a program counter. For example, this is an add. But you operate on multiple different data elements. So how do you know how many data elements you operate on? There's another register. That's the vector length. That tells you, oh, I should operate on 4 elements. So whenever I do a load, for example, I calculate a base address, and this vector register says, oh, load the 4 elements starting from that address. So you really do 4 loads to different locations, starting from that base address. And we'll see this in more detail soon. So basically, this little instruction that doesn't consume much space gets expanded to many operations internally in the processing element. So VLIW is like this. You still have the encoding overhead. But of course, there's an advantage and disadvantage. The advantage here is irregular parallelism, right? You can exploit irregular parallelism here, whereas you have to rely on regular parallelism, data level parallelism here. Okay, so let's look into some example here. So a vector, hopefully you know what a vector is. It's a one-dimensional array of numbers, right? And many scientific commercial programs use vectors. Hopefully you programmed with vectors. How many of you did? Okay, good. So you know the concept from math. But this is an example computation. I cooked it up. Basically, for 50 elements, you average 2 different vectors, right? Element by element. So it's really element-wise average of 2 different vectors. And store the result into C. So a vector processor is one whose instructions operate on vectors rather than scalar, single data values, right? So if you encode this in a single instruction, single data, I say you have a lot of instructions. So first of all, you need to fetch all of those instructions every other cycle, right? So basic requirements, let's look at the requirements first. You need to load and store vectors. So you need vector registers that contain vectors that I showed you earlier. You need to operate on vectors of different lengths, because you may not always have an array that's 64 entries, right? Actually, sometimes you have 512 entries, which means that you need to stage them into the 64 entry register. Sometimes you have 4 entries. So you need to have a vector length register that specifies how many elements should this instruction operate on. And your vector length can change. So that's an instruction. You have an instruction that changes the vector length. And elements of a vector might be stored apart from each other in memory. So you need a vector stride register. This will become more clear, but basically stride is the distance between 2 elements of a vector. Actually, I'll give you an example right now. So you need to, whenever you're doing a load, you need to know how far away these elements are from each other. Consecutive, right? So let me give you an example of matrix multiplication. You guys have done matrix multiplication, I assume, right? So in a matrix multiplication, if I can do this correctly, so let's say this is M things. So you'd better have M over here, right? What you do is you basically take a dot product of this and this, right? So let's assume that this is M is equal to 64. And you lay out the matrix in row major order. So this is row 0, row 1, row 2, ... Which means that consecutive elements in the row are in consecutive locations in memory. And let's say the base address is A over here. And then let's look at the view of memory over here. Memory is a linear array, and A is here. And we're going to have row 0, element 0 starting at A, row 0, element 1 starting at A plus 1, row 0, element 2, A plus 2, ... all the way to 63. And row 1 starts at A plus 64. So that's the row major order. Consecutive elements in a row are in consecutive locations in memory. So you have basically row 0 here, row 1 here for A, and then 0th element, 1th element, ... So when you're loading this vector, this row into your vector register, your stride is 1, right? The distance between these elements is 1 in memory, right? Memory address A, memory address A plus 1, A plus 2, A plus 3, ... So the load instruction can compute its address nicely. But if you look over here, if you store this also in row major order, and now let's say we have n equals, well, I guess in this case it doesn't matter. Okay, let's do something over here. Let's say we have, I'll say this is columns. Columns equals, I don't know. Shall we say 10? 10 sounds good to me. So you have 10 columns over here. Now if you store this in row major order, let's say this starts from address B, the first element of this row over here is at 0, 1, 2, ... So you have the 10th element, 10th element over here at address 9. So if you look at memory over here, this matrix starts at location B, And its first row is here of 10 elements, and 0, 9. Next element is at 10, and then 19 over here. Next row starts at address 11, b plus 11. Assume all bytes here. Oh no, 20 sounds better, right? 29, and then 30. Now, you want to multiply this with this. So when you load this, you need to load 64 elements with a stride of 1 starting at address A. So it's a vector load, address A. And you need to set your, before that, you need to set your vector length to 64, and you need to set your vector stride to 1. But if you look here, you want to load all of this into a register. Let's assume that you want to load 64 of these. And actually, M is conveniently 64. That's nice. When you need to do this load from B, vector load from B, you need to change, vector length is the same, that's good. You don't need to change that, but you need to change the stride to 10, right? Why? The consecutive elements that you're loading are 10 locations apart in memory. Because you've laid out your matrix this way, right? Does that make sense? So you really need to change the vector stride. That means that your load translates to the first element that you want to load is from address B, and then address B plus 10, B plus 20, B plus 30, and you do it until B plus 10 times 63. So basically, oh, you cannot see it. Yeah, now you can see it. Basically, your vector load really translates to a for loop where you go from I equals 0, I less than vector length, I plus equals stride, or vector stride, load into vector register, I guess B, I, right? So if you want to write in high-level language, that's exactly what you're doing here. It's basically a for loop load, and you need a stride because consecutive elements may not be in consecutive locations in memory, and clearly in this case they're not. So this will have impact on performance because you're accessing not sequential locations in memory, but some other locations in memory. So keep this in mind, but that's the concept of stride. Now you have a stride over here. It's really the distance between vector. Okay, I guess we'll have to leave the example for later, but let me give you why this is useful. A vector instruction performs an operation on each element in consecutive cycles, and you can pipeline the vector functional units. So vector functional units can take lots of different operations, and each pipeline stage operates on a different data elements. And vector instructions allow deeper pipelines because there's no dependency between these data elements, right? They're completely independent of each other. You're just doing the same operation on different data elements. There's no control flow, and you have a known stride. Okay, I think I'll stop here because we'll need to go into a detailed example of how this operates and how this outperforms a pipelined processor that's scalar. But now you can, I'll leave the slides for next week online, so you can study it, you can take a look at it on your own. Okay, have a good weekend.